this video, we're going to dive deeper into how neural networks and machine learning actually works behind the scenes. And if you're learning machine learning, you've probably come across a diagram that looks like this, which oftentimes, if not most of the time, confuses people because it's a bunch of circles and arrows, and the explanation is usually just as confusing. Well, it's simple. You take your input circles and move them through your circles, and you end up with your, voila, neural networks. And so that's not really a very good explanation. At least it wasn't very good for me when I was learning. So hopefully we're going to break this down, make it really simple, because it's not really rocket science going into this. It's not simple like ABCs, but it's not super complex either. So if you watch this video a few times, it'll give you a big head start on what neural networks are, and maybe even you'll be able to go and code some yourself if you have coding experience. So here's the picture of the neural network. We're actually going to use this diagram later, but you're going to understand it. So a good way to start is to block off this center layer. We're going to call that the black box. And this is what we've been doing if you've been watching my last two videos on machine learning. Let's just stick to the input and output data, the training data, right? Given this information, here's the outcome. These are our input dimensions and the outcome dimensions. And then somewhere that black box in between runs over that information over and over and over again. And each time it has 1,000 knobs on that black box, and it twists a little knob just a little bit at a time until, wow, the black box is tuned and we can give it new input information and get the correct predicted outcome. And so this video is going to dive into the hidden layers area, that black box, and how we configure it and what it does. So there's some common configuration options, no matter what machine learning or neural network library you're using. There's some common configuration options that you're going to come across for configuring that neural network. One, how many hidden layers do we put in that black box? We know we have an input layer and an output layer. How many layers go in the middle? And usually one is where you need to start off with. That's pretty simple and straightforward. And then how many nodes, how many neurons go in that hidden layer? And there's a few different ways you can kind of give yourself an answer to that. There's not an exact science to it. A good path is if your input and output dimensions are drastically different, go somewhere in between. If you have 7 input values and 2 output values, then maybe 3 or 4. Also, you definitely want it to be less than 2 times the input nodes. If you get bigger than 2 times the input nodes, you can get a situation called overfitting, where you're just not going to get accurate outcome. Also, 2/3 the input nodes plus the output nodes, that's a good kind of way to go. And so if you kind of run the math on these 3 situations, you'll kind of get some ideas on how many nodes that hidden layer should have. An activation function. This is very important, but I'm not going to go into it right now. Also, learning rate and momentum are important, but I'm not going to go into those right now. Lastly, the iterations and the desired error level. So iterations is how many times it goes over all the data in your data set. The desired error level is how accurate do you want this thing to be? And depending on what you're going for, basically training stops until you get to one or the other, till you've gone through, say, 20,000 iterations, or until your error level is 0.0001 and it's pretty accurate. Whatever you set, the training's going to go till you get to one or the other of those. So that's the configuration options. That's actually not too bad. That's how you tune your black box. So if you have a little bit of knowledge as to what the black box is doing, you can usually tune a neural network and move on from there and get good results. So let's go to a real example using these circles and arrows that we have from before. We have a data set. This data set gives us fur color and weight of animals, and also tells us if those animals were who's its or what's its. So we want to go through all of that data, train our neural network to predict who's its and what's its based on fur color and weight. And so we've chosen 3 hidden layers based on the options that we showed you on the last slide. So let's go ahead and then get our neural network initialized. So to start off, we basically want to create a stupid brain, a brain that knows nothing. So we're going to just randomly create a bunch of weights. You can see, I'm going to get my mouse out here. You can see we've assigned a 0.1 weight, a 0.3 weight, just completely random numbers. And these neurons, these hidden layer neurons and nodes, are going to also get a bias. Consider them coming in with an opinion already, even though we don't know anything about how fur color and weight apply to who's its and what's its. We're just going to start making guesses based on our bias. Consider them the liberals, conservatives, and libertarians, and we're going to get them all in a room, show them a bunch of real life data, and hopefully at the end of the thing, they'll all agree on what is truth. I'm not going to say anything. Okay. Nope, not going there. Moving on. So that's our hidden layers. We initialize the network with just a bunch of completely random weights and biases. And then moving on from there, we're going to start with the first entry in our data set. So entry number 1, we have an animal, fur color 25 and weight of 15, and it's a who's it. It's a who's it 1, it's a what's it 0. So now we start moving these input dimensions through the neural network. It's called a feed-forward neural network for that reason. So basically what we're going to do is we're going to take both of the input dimensions, we're going to multiply them times the weights, and then add the bias. So here we go. Node 1 gets fur times 0.1 plus weight times 0.8. See, we have our 0.1 weight and our 0.8 weight. And then we're going to add the 0.71 bias. So that's node number 1. So we're basically saying, let's randomly guess how these two nodes affect our outcome. Let's just start with a guess. And then we're going to do that for each node. A completely different set of weights and biases here. A completely different set of weights and biases here. You can see when we get down here, we're taking fur times 0.57 plus weight times 1, and we're adding a 0.09 bias. So we're basically making a random set of guesses, and then we do the magic. And then we run all those through an activation function. And here's where the activation function is important. Here's where the magic of neural networks comes in, is because we're trying to figure out answers to nonlinear data. And so I'm going to do a little bit of a tangent over here and kind of show you the difference between linear and nonlinear data. Linear data is a straight line. We can say that, hey, as the weight and the fur color goes up, we know it's a greater chance of being a who's it. As it goes down, it's a greater chance of being a who's it or what's it. Or, hey, if the fur color's high or if the weight is high, it's always going to be a who's it, right? So you could use this with some species. If it's big, it's a dog. If it's small, it's a mouse. If it's smaller than a certain size, there's no way it's going to be a dog. That's linear information. You don't really need a neural network to solve answers on these. You just need a little bit of math, and the data should be pretty clear as to how the input correlates with the output. Nonlinear is like this. It just turns out differently. It may be high here and high here, or it may kind of follow some unusual curves that are really difficult to figure out on your own. And so that's basically where your activation functions come in. We're going to use a sigmoid or a tan or tan H or a tanch, depending on who you are and where you come from. And so we're going to basically apply that sum value. We're going to run it through one of these functions and introduce nonlinearity to our neural network to help us kind of find out the answers to those questions. So we've taken the sum, right? We've taken the sum times the weights, and we've added in our bias, and we're going to run that through our activation function. Now we're going to get a nonlinear guess here. And then we're going to continue running through until we get to our outcome. And let's just throw out a number here. Let's say we ran it through our activation function, came through again here, and we end up with just a random drawn out of the hat guess that it's 0.3512, that it's a who's it, and 0.781, that it's a what's it. Completely wrong, right? Our neural network is stupid. It came in with just biases and random numbers and made a guess that was way off. So then it's back propagation time. We're going to calculate the error and the delta, which is the difference, and we're going to adjust all the weights and the biases. We're going to go backwards through each step, and we're going to adjust these biases and these weights some. We're not going to necessarily adjust them all the way, but we're going to adjust them some. How do we know how much we're going to adjust them? Well, we do that through our configurations. The first one is learning rate. Learning rate says how much should this step outcome affect our weights and our biases. And learning rate is, you almost want to think of it as personality types. There's the slow calculating type of person where if you were to show them, here's a cat, here's a dog, they're going to say, I have some ideas. Show me some more. And then after you show them a whole bunch, they'll slowly lean into the answer and then come up with a very calculated answer. That's a low learning rate. A high learning rate, a ridiculously high learning rate, would be, oh, you showed me a cat and a dog. I calculated the differences between the two. I know the difference. And then you show them a really fluffy cat and they think it's a dog because they had way too high of a learning rate. So that's what learning rate is. And then momentum also says, how should our past outcomes affect our weights and biases? So past outcomes could say, hey, that initial weight there keeps giving us way too high of an answer. So we're going to keep that weight kind of going downward no matter what. At least we're going to give it a little bit of momentum into this next step. So each step kind of takes learning rate and momentum into account. And we don't just want to make snap judgments. And we also don't want to learn too slowly, because if we learn too slowly, it takes forever to train our neural network. So, right, it's kind of that balance between how fast do we want to train our data versus how accurate do we want that data to be. That's kind of where your learning rate and momentum come from. So here's kind of an example formula. We're going to take our learning rate, we're going to multiply it by the difference, and then multiply it by what the actual value is now, and we're going to add that to our momentum times our past change amount, and that is our current change amount. So that's kind of an example formula for how we use learning rate and momentum to determine how much to change a given weight and a bias. So now we go through the next piece of data. Yay, we did it. We did one iteration through the first piece of our data set. We're not through our iteration yet. We're going to go to the next piece of our data set where fur color is 15 and weight is 35, and that's a what's it. And so we do that through each piece of data in our data set, and boom, that is considered one iteration. So we have an iteration, and we have an average error rate there. And then we can determine, do we go through and do more iterations? Have you requested more than that? Or have you requested that to be an acceptable error rate? And if not, then we just keep going. So that's how you train a neural network. You give it inputs through the random weights, which get more accurate over time, biases, activation function, which is huge, and then you're going to calculate your error, and you're going to back propagate some adjustments here to the weights and biases. And when you're done, you get a set of weights that are accurate, a set of biases that are accurate, and you can then run any input into it. It goes through the weights and biases, and you get a pretty good guesstimation of what that output's going to be. And that's neural networks and machine learning in a nutshell. I hope this video helped. In the next video, we're going to actually go back to Brain.js and watch all these configurations and all these options in action.